Hey guys, I'm at City Hall using their electricity on day 3 after the hurricane. So I'm gonna pick up where we left off. Hopefully you can hear me. There's a big semi truck giving out ice behind me, which is awesome. So anyway, let's get back to business here. Okay, so if you had something hanging from your rear view mirror and you're accelerating forward, and your velocity is forward also. The thing hanging on the rear view mirror will be appeared to have a force that pushes it towards you. It will lean towards you. So let's see what we got. How many forces are acting on the bottom of the pendulum? Okay, well, let's erase that one. Okay, so we know, forces we know for sure. There's tension. There's tension in the rope, in the chain, string, whatever. There's weight, and that's all. That's all there is. Now, there's apparent force pushing it this way. Okay, apparent force. It's not really there, but the car is pushing ahead, and the rosary or whatever that's hanging is being held back because of inertia, the first law of motion. So, let's see, we break this up into X and Y components. This be TY, this be TX. And that angle there would be the same as that angle. Okay. So our job is to find how many forces are acting on the bottom of the pendulum. So, like I said, this force right here is not really a true force. That's the apparent force. A-P-A-R-E-N-T, apparent. Okay, but it seems to be like a force because the object is trying to remain at the same speed the car had before it accelerated. So let's pretend there is a force there, but really there's only two real forces acting on it, the tension and the weight. What's the size of the net force? Well, so net force is equal to, I'll put this as the apparent force in quotes. So it's equal to that. It's equal to mass times A. Second law is equal to 0.5 times 4, because there's the acceleration of the car. Okay, so that would be 2 newtons. What is the strength of the tension? Well, gotta use some trig here. Okay, so the tension, I'm gonna pick this triangle right here. Okay? So I got this triangle. This is the tension. And I know the x component because Tx has to equal that fake force right there if the thing's at rest. Well, relative to the car, it's at rest. The rosary that's hanging from the dashboard, from the rear view mirror. Okay, so that is equal to 2 newtons. So we can use some trig. That's like the x component. So remember that Q equation, Q x equals Q cosine. Well, in this case, it's the opposite side. Tx is the opposite side, so this would be really like Qy equals Q sine of theta. You can see that that's the opposite side, right? So Tx is really the y component. It's not the y component, it's the opposite side. Is equal to T sine of theta. And so we know that's 2. Tx is 2. T, I don't know. Then sine theta, but I don't know what theta is. Well, look, we do know we can find what theta is, or we can find T another way. Okay, so we're not going to be able to do this because I don't feel like finding the angle. So this is Ty right here. This is T, and this is Tx. So I only know Tx. Now if I can find Ty, I can solve for what T is using Pythagorean theorem, right? I got 2 legs of a right angle triangle, so I can find the hypotenuse. So let's find Ty. Well, Ty is easy. Ty is equal to the weight because there's no net vertical force. So Ty is equal to the weight, and I already have that. So 0.5 is the mass times 10, so that's 5 newtons. So we have Ty is 5. We got Tx is 2. We got the hypotenuse T is equal to square root of 5 squared plus 2 squared. I get 5.39 for the tension in the string. Okay, so now we can find the angle easily. Angle is equal to, here's the angle. Okay, because this is not from the x-axis. I gotta flip around my cube rule. So this is the inverse tangent of the opposite, which is Tx. Here. Opposite over the adjacent. So this would be inverse tangent. Tx happens to be the opposite, not Ty. 2 over 5. And I get 21.8 degrees. Okay? So that's kind of tricky because Tx, this force is an apparent force. Also, the angle is, again, not from the y-axis, not from the x-axis, so we have to switch around our x and y's in the equations. Okay, so here's another problem. What's the net? They gave me all this stuff. What's the net force? So net force is an apparent force pushing it that way. Because so net force, because this, now why is it moving it that way? It's because the car's decelerating. The velocity is forward, but he's putting on the brakes. So the pendulum appears to be pushed forward. It's an object that's moving in motion, and it wants to remain in the motion it had before the car braked. So there's a net force, apparent net force forward. So the net force will simply equal m times a. The mass, oh, be careful. If the weight is 7 newtons, weight equals mg. So 7 equals the mass times 10. Don't put weight for mass. Mass equals 7 divided by 10, or 0.7 kilograms. So we got the net force equals 0.7 times the acceleration, and the net force, because the pendulum's really not moving as the once it swings forward, the net force is equal to Tx, which is giving us 3.5. So 3.5 equals 0.7a. So the acceleration of the car is equal to 3.5 divided by 0.7. So that comes out to 5 meters per second squared. Actually negative because it's slowing down. Okay, when you do a dynamics equation, you don't put the negatives in until you get to the answer. So acceleration of the car is negative 5 meters per second squared. I'm sorry, I didn't write the net force. Net force is equal to Tx, 3.5 newtons. I wrote that right here. Okay, it's the car speeding up, slowing down. Well, the car's slowing down, and the pendulum is retaining the same speed that it had before the car put the brakes on. So it's slowing down. Okay, these are reviews again of the elevator problems, and it's important you can do these. I don't know why I'm doing it now, maybe as a review. So there's her mass. Now scale measurement is always going to be the normal force. So when she moves at a constant speed, that means constant speed means acceleration equals 0. That means the net force equals 0. That means that lady right there, the normal force has to equal the weight, because they balance each other. So that's a scale reading. So she's moving at constant speed. There's zero acceleration. There's zero net force. And the normal force, the scale pushing up against her, is equal to her weight. So that would be mg. So 65 times 10 is 650 newtons. Okay? Scale would read what she normally weighs. What is she's moving at constant speed downward? This is a different color. Well, this holds the same. This holds true. If you're going constant speed, acceleration is zero, net force is zero. Normal force equals the weight. So it's the same. The scale will read the same amount if she's at rest. What? The scale will read the same as her weight, whether she's at rest, whether she's moving upward at constant speed or moving downward at constant speed. Okay, how about letter C? Where she accelerates upward at a rate of 2.4. Okay, so she's going upward. There she is. There's going to be acceleration equals upward, positive 2.4. So the net force will be upward. That means the normal force is going to have to be bigger than the weight. The weight doesn't change. Her actual weight doesn't change, but the normal force will. Okay, this is when you feel smushed in the elevator if it accelerates upwards quickly. So N, normal force is greater than the weight in this situation. So let's find what the scale reading is. Well, net force is up. Oops, I like to write net force. So net force is the bigger force, direction of the acceleration, minus the weight. So net force equals MA. Her mass is 65. Yep. Her mass is 65. The acceleration is upward 2.4. And equals the normal force, which I'm solving for, minus her weight, which I already solved over here, 650. So when I solve for this, I add the 650 to the left side. The normal force becomes 806, which is greater than her weight of 650. So she's the scale is pushing up with a greater force than she's pushing down, so she feels like she's getting smushed against the floor. Then letter D, well, she accelerates downward. Okay, so letter D, let's do that here. Basically, it's the same idea, except that acceleration is downward. So the weight's going to be bigger than the normal force. So the net force is still going to be MA. We already solved that up here. And that equals a bigger force, which is a downward force because the acceleration is downward. So it'd be weight minus the bigger force minus the smaller force. So it'd be 650 from before, her weight minus normal force. So I'm gonna add normal force to both sides. And so rewrite this. See, oops. So I rewrite this. Okay, 65.2.4 is 156 plus n equals 650. So n equals 650 minus 156. So we get 494. So how's she gonna feel on that elevator ride at this point? Well, her normal force, the floor pushing up against her, or the scale pushing up against her, is less than her actual weight. She's gonna feel kind of lighter, like kind of closer to weightless. Now, so we just did letter D. So letter E, I'm going to ask you, what if she was freely falling? What would be the normal force? Well, if she was freely falling, the only force acting on her would be her weight. Normal force would not exist. So what would be the normal force? Normal force would equal 0 if she's freely falling. Okay, so I add that question. Okay, so they solved this for you. Maybe you want to see how they did it, but I did all that. Okay, now what's coming up is new. This is when you have more than one object connected by a string or something. So I don't know why this hand's way up here. This hand is moving this string to the right. The applied force, positive physics calls it A. Draw a free body diagram for box A. Okay, well, first of all, you gotta realize that according to Newton's third law of motion, box A is pulling on box B with the same force that box B is pulling on box A. Okay, those are independent of the applied force. They don't equal the applied force necessarily. It's pretty easy because there's no friction. So we don't have to draw forces like going this way. We will eventually. Okay, so the force, applied force is 40 newtons. Okay, this is 10 kilograms mass. This box B is 12 kilograms mass. Now, draw a free body diagram for box A. Well, box A has applied force, and I'll call that tension. Okay? Even though applied force is a tension too, but I'll just call it A. And this is box A. So I'll just say 12 kilograms inside. You don't have to do that, but it makes it clear. In box B, this has one horizontal force acting on it. And that's the same as this T right here. The opposite direction though. Okay, of course, there's the weight of box A and normal force on box A. And there's a slightly smaller weight for box B and equal normal force to its weight for box B. Okay, but I don't really care about the vertical forces because why? Can you think why? These vertical forces cancel out. So I don't really even need to consider them. Find the acceleration of the two boxes. Okay, here's the trick. Each big T, the tension in the string right here, between them, connecting them, cancels out. Because one's negative, one's positive, and they equal each other. So basically, if you smush the two boxes together, the tensions cancel out. And we can treat this as one object being pulled by the applied force. Find the acceleration. Okay, we know the applied force is 40. It's given. So the acceleration of block A is the same as the acceleration of block B because they're connected by a string, a non-elastic string. So the acceleration is the same. So we can do net force on the system, the two connected boxes, is equal to the two masses, 10 plus 12, times the acceleration. Okay, we know that the net force on the system is the applied force 40. So find the acceleration of either box is 40 divided by 22. It comes out to 1.82 meters per second squared. Now either box has an acceleration of 1.82 meters per second squared to the right. Now find the tension in the cord between box A and B. Okay, now what you do is you go to either free body diagram, either one. Okay, so I picked the simplest one, which is that guy. So I'm trying to find the tension. So this is pretty easy. I don't care about the normal force and the weight because they cancel out. So we can say the net force on box, what was that? Box B is equal to MA. So equals 10 times the same acceleration that we had before. And so that's 18.2. That's what the tension is. Okay, right? I should have said that. The net force is a tension. Because there's no other forces acting on it that aren't canceled out. Again, the N and the W are canceled out. So, I mean, you don't have to prove it, but we can. We can do the same thing with box B. I'm sorry, box A. Okay, the mass of box A is 12 times, I'm sorry, oh, wait. But F net for box B would be A minus tension, so it's a little more complicated. So this would be the applied force minus the tension. Equals the mass times the same acceleration, 1.82. Okay. I know the applied force is what, 40? Okay, 21.84. So the tension is 21.84 plus 40. Well, that's negative tension. Let's be careful. So let's add t to both sides. So 40 equals 21.84 plus t. So t equals 40 minus 21.84. I get 18.16. Now, if you look at these two answers, they should be identical because the tension in box B's string should be the same as the tension in box A's string. And because I'm rounding things, they're not exactly the same, but pretty darn close. Okay, so you don't have to do that. You can just do one of the boxes and find the tension, because the tension is the same in both strings. I'm sorry, it's one string. The tension is the same on both ends of that string because of Newton's third law. Okay, so these notes go through all the junk I just said. Okay? So basically, if you want to go through that step by step, I don't think it's as straightforward. Okay? So it goes on. Now, here's a cute little equation for finding the acceleration. If you want to memorize that, go ahead. But I mean, I can derive that equation from what I did step by step. So it'd be the applied force over the sum of the masses. That'd be the acceleration. This means sum of intentions. They have a cute C-low equation? No. Okay, so here's another example. If they're pushed together, no string, it's the same kind of idea. So if I draw a free body diagram for each box, box A has the force of B pushing against it and the 30 newtons here. I'll call that the norm. It's really a normal force because it's pushing against it, but that'll be confusing. Let's just call that. It's not tension, but I'm going to do it anyway. Just not to confuse things. Or if I feel I'm doing something wrong there. So let's call that. Let's call that F. The force of B on A. Okay? Force of B pushing against A. Okay, so force of B against A. Okay, and then box B would be, okay, it would be force of A pushing against B, and that's it. The 30 newtons is not affecting, it's not directly applied to force box B, so don't use it there. So that'd be the easier one. Now, these two guys have to equal, these two forces, contact forces, have to equal each other because of Newton's third law of motion. Okay, so we just did these two things. Now, really, if you were doing free body diagrams, the forces should come out of the object, point away from the object. So I'll do that big deal. FBA is this way. this one would be okay. So you really should make the forces always pointing away from the object. Draw the acceleration. Find the acceleration in two boxes. Okay, we smush these two together. So acceleration of the system or of either box, it's the same thing. Acceleration equals net force. Here, let's do it this way. Net force equals MA. Okay, so net force. Okay, this is equal total mass of the system's mass of A plus mass of B times acceleration. And net force, there's only one force because these two guys cancel out. There's only one net force. That's 30. Okay, so what we got is 30 equals, what's mass A and mass B? 5. And mass B is 8 kilograms. So 5 plus 8. So the acceleration of either box is 30 divided by 13. I'm getting 2.31. And that would be to the right, of course, in the same direction as the net force. Okay, so that's find the force on box A and B. Okay, so that's all they do. So find one of the tensions, even though they're not tensions. So pick the easier box. The easier box is this guy. So let's find this force right here. Well, if you select just box B, the net force on box B, this is a system over here. The net force on box B is equal to mass of box B times acceleration. We already know the mass is 8 kilograms. Acceleration we just found, 2.31. So 8 times 2.31 is 18.38. So it's 18.5 newtons pointing to the right. That is the, where is it? That would be force AB, which is the force on system B. Now that's what they're asking for. No, they're asking for FBA. Well, it's the same thing, but to the left. So force BA is 18.5 newtons to the left. Now you don't have to prove it like I did before. You don't have to prove that like I did before. Okay? So you can go through all that stuff if you want. Okay? Now, these things are very similar at Wood's machine. This is a pulley right here. A pulley. There's one string across the pulley. One string. And it just, these are free, these weights are free to move up or down because they're connected to a string. It's called Atwood's machine for some reason. Okay, mass A is 20 kilograms. And mass B is 50 kilograms. Fine. They are held at rest and then released. Okay. Draw a free body diagram of each mass. Okay, so by definition, these two tensions have to be the same. Okay, by Newton's third law of motion, A is pulling on B with the same tension that B is pulling on A. Okay, so let's draw a free body diagram in each situation. Well, we got the weight of A and we got the tension. That's for block A. Block B, we got the weight of B, which I'm going to make it a little bigger because I think it's heavier. Yep, much heavier. I'm going to make it bigger than WA, but I have to make the same tension. Same tension. Okay, those are my free body diagrams. Find the acceleration of two masses. Okay, what I do is I look at it as one thing. There's the two T's. I kind of pull it, so I pull these two blocks and I straighten it out to make it look like the problems we just did. So here's WA, here's WB, and then here's my two T's, which cancel out. So basically, the net force, I'm trying to find the acceleration of the system, which is the same as the acceleration of either block. That's the net force of the system times the mass. F net equals ma, Newton's second law. Okay, so net force would be the bigger force minus the smaller force. So bigger force is WB. I mean, I can find that right now. This is mg. This is 50 times 10 is 500. And the smaller force is ma times g, which would be 20 times 10, which is 200 newtons. So this would be WB minus WA because WB is heavier. So 500 minus 200 equals the total mass. 50 plus 20 times the acceleration of the system. So this would be 300 equals 70A. A equals 300 divided by 70. And we know that the acceleration of either block is the same in magnitude, but one's moving downwards and one's moving upwards, of course. The lighter one always moves upwards. The heavier one always moves downwards. So 300 divided by 70 gives us, 4.29 meters per second squared. Now if you get 9.8, you're wrong. It can't accelerate faster than free fall speed, which is 10 meters per second squared. Okay, so that's the acceleration of either block or the acceleration of the system. Okay, finally, find the tension, either one. So either one's just as hard, just as easy, I should say. So I'm gonna pick one of them. one of these blocks. Either one's just difficult, so I might as well pick this one. So here's the weight of A. The weight of A is 200. Now notice I'm not putting negatives on weights because in dynamics we use our free body diagrams. We don't use negatives in the equations I'm using. Okay, this would be the tension. This is A. Okay, so what am I trying to find? The tension. So net force on A, it's not the same as the net force on the system. Actually, the net force on A and the net force on B will add up to be the net force on the system. Okay, so I didn't say that before, but okay, so let's focus. This is mass of A. Oops, that's before we do this. The net force on A is equal to, okay, A's moving upwards. So T has to be greater than the weight in this case. Now, for the other one, the weight of B is greater than the tension. But I'm not doing the other one. I mean, I could. I get the same. Answer for the tension if I did it for B. Block B. Okay, so the net force on A is equal to T minus the weight. So this equals M times A. The mass of A is 4.29. The acceleration of A, oops, that's the acceleration of A. The mass of A is 20, not 200, that's the weight. That equals T minus 200. So tension equals 20 times 4.29 plus 200. That equals 285 newtons. No, actually 285.8, so it's 286 newtons. Okay, so if I do the same thing for the other block, I get the same answer for the tension. Okay, what else do we got here? Okay, so they explain that. They explain it. Okay, I don't like these little shortcuts because you'll get them confused and you cannot write them down on your equation sheet. No, you cannot. Okay, what if you had something like this? Something with, oh, now they got friction. And they got a block that's hanging over a pulley connected by a string to the other block that's dragging across the table. This is a good problem. Okay, so these two tensions, let's just call them tensions. Okay, I'm not gonna mess this up. Okay, so draw. Okay, so we got friction. You know what? I'm just gonna call these tensions. Call that tension. Tension. I'm gonna call this weight B. I'm gonna call this weight no. I'll call that little friction. Okay, so I'll use the blue letters instead. Okay, so obviously we do have weight here, the weight of A and normal force of A, because that block is resting on the is on the table, and the surface of the table is pushing up against block A. But this guy, B, block B has no normal force, right? Because it's not resting. It's not on a surface that's pushing up against it. Okay, so these two tensions have to equal each other because of Newton's second law. No, third law. Action-reaction law. Okay, so let's draw the free body diagram, box A. Even though I just did, we got tension, we got normal force, we got weight, and then we got some friction. Okay, they gave me the coefficient of friction, the coefficient of kinetic friction. Okay, that funky symbol, that's not the friction. Let's find that right now. The coefficient of, no, friction is equal to the coefficient times the normal force. So this friction is equal to 0.2, and since there's no diagonal forces acting on it, the normal force equals the weight. Here, let's write that. The normal force of the block is weight A equals mg, which would equal the mass of block A is 5 times 10 g. So this would be 0.2 times 50. That's what the weight is. That's what the normal force is. So 0.2, the coefficient of friction times the normal force is 25 newtons. So I had to do that work to find the friction. Okay, so now I can skip the WA and the weight A and the normal force because they cancel each other out. I just needed the normal force to find the friction. Okay, let's do the same thing. Find the free body diagram for block B. Well, that's easy. You got WB here. Now I'll do that. And so block B is 2 kilograms. 2 times 10 is 20 newtons. And then we got the tension going up. Now, basically, I'm going to straighten this out. Here's A, here's B, and it's really not on a, B isn't on a table, but I'm just going to draw like this. So there's the two tensions that equal each other. There's the friction on A, and there's the weight of 20 newtons. Weight B of 20 newtons. So friction equals 50. Weight B is 20. Bing, 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 bing. Mistake, 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 mistake. So you probably were wondering. This is, I did it wrong. That's 10 newtons. So friction is 10 newtons. Sorry, I miscalculated. Okay, so find the acceleration of the system. So net force of the system, or the acceleration of each block, same thing, is equal, smush them together, okay, we're looking for the acceleration of the system. So net force on a system is the bigger one minus the smaller one. So it's 20 minus 10 newtons, which is 10 newtons. You get the total mass of the system is 5 plus 2, which is 7. Add the two masses times A. So 10 equals 7A. A equals 10 over 7. 10 divided by 7 is 1.43 meters per second squared. Okay, that's the acceleration of either block or the acceleration of the system. Find the tension in the cord. Next, find the tension in the cord. So, let's pick the easier one. Nah, nothing's easier. So, it doesn't matter who you pick. A or B, I'll pick A. So, we got tension here. We got friction here. This is A. Tension, I don't know what that is. Friction is 10. Okay, it's very important that you don't think the net force that we just found, 10, is the net force on the net force of the system is not the net force on the individual parts of the system. So you gotta find that. So the net force on A is equal to tension minus, because it's moving to the right, tension's bigger, minus the friction. Now this is mass of A times the acceleration of the system, because the system's acceleration and the individual parts of the system's acceleration are the same because they're connected. Okay, so tension minus 10. So MA, mass, let's see, what's the mass of A? 5 kilograms. 5 times acceleration, 1.43 equals T minus 10. T equals 5 times 1.43 plus 10. T equals 17.14 newtons. And you could solve it for the other one, block B, if you want to, but not necessary. Okay? So let's see what else we got. This explains it all if you want. Wow, it's a lot of explanation. And again, what good is that equation? Okay? I like to do it piece by piece. Okay, so here's one from positive physics, and we'll end with that. Well, we'll save those two for another video.